In this video, I am going to explain about the limit cycle oscillation. For a stable IR filter, the constant input is expected to give a zero output. But due to the quantization of multiplication, the output tends to oscillate between a fixed range of signal. This is due to the non-linearity of system and it is called limit cycle oscillation. I'll explain in another way. I'll select an IR system that is X of n that is giving you the output Y of n, and this Y of n is connected back because it is an IR filter, a recursive filter. So one time feedback, that is one time the previous data is taken and I'm multiplying that with a constant A, and this is connected back to the input. So this system is called as ideal system, that is Y of n is equal to A into Y of n minus 1 plus X of n. This kind of systems, that ideal systems, the limit cycle oscillations won't be occur. There won't be any limit cycle oscillations for this IIR system. I'll select one non-ideal system, that is non-linear system. That is, I'll select the text of n, that is directly giving that output y of n. I'm taking one time the past data, that is y of n minus 1, and this is again multiplied with A. Once the multiplication is over, immediately the quantization will be taking place and the quantized values are added with input and giving you the output. So y of n is equal to A into y of n minus 1, and this is going to be quantized and then added with x of n. So this kind of system will produce limit cycle oscillation. What is that quantization? So usually in all the digital signal processor, to store the results, we will perform various arithmetic operations. To store the results, we have fixed size register. So we have a fixed size register. When you are performing multiplication, sometimes the result may be some infinite representation. When you are multiplying two 8-bit numbers, sometimes there may be a chance we will get the answer is 16-bit. So in that case, we have only 8-bit register to store the answer. For example, I have got the answer for the multiplication, that is a into y of n minus 1 answer. I got it as 0.00001000101. Okay, but I have only 8-bit register, so I can able to store only 8 bits. Okay, so 8 bits, but it is having 10 bits. So what we can do is we will write only that, we will store that 8 bits alone in the register. We will cancel this last 2 bits. This is called as truncation. And we will check the 9th bit. For example, I have the same input. I'll do a small modification. If suppose I'm having this representation, after the product or after the multiplication, I'm getting this representation. So I'm checking that 9th bit. If the 9th bit is 1, I'm going to add that with the previous bit. So 0.000010001. So this is called as rounding. So anyway, the truncation or rounding, that is a wrong representation from the original. So right, so this is because of the finite word length or finite or fixed register size in the DSP processor. This is called as finite word length effects. Usually the quantization is this truncation or rounding. So because of this truncation or rounding, so because of this error representation, the answer is always oscillate between certain ranges of signal, that is named as limit cycle oscillation. So we will check the characteristics of limit cycle oscillation with an example. So I'll select one example. Let y of n is equal to x of n plus a y of n minus 1, where a is equal to 1 by 2, x of n is equal to 0.875 at n is equal to 0, 0 otherwise. So except n is equal to 0, all the other place the input is 0. The system is quantized with, the system is quantized with 3 bits and a sign bit. Determine the limit cycle value. Determine the limit cycle value. So the given equation is for ideal system or ideal filter, but that limit cycle oscillation will be happening for non-linear system. So in that case, we need to perform the quantization. So I'm going to write that equation little bit modification with that quantization format, or the quantization representation. So y of n is equal to x of n plus, when there is a multiplication, definitely if it is within that required bit, no problem, we don't need to perform the truncation or rounding. When that value is greater than the available bit size, we need to perform the quantization. So in that case, it is quantization of a into y of n minus 1. So now, to determine the limit cycle value, we must know what is that y of n for various durations. So for that, I'm going to select various n. Every time I'm going to calculate y of n. The y of n is a combination of x of n and the quantization of y of n minus 1. So every duration I'm going to calculate what is the corresponding input for the particular n and what is the quantization value for this particular time. So when you are adding both, what is the resultant y of n for the particular time. So likewise, we are going to calculate that output for various durations, and finally we are going to verify how that limit cycle characteristics are or how the limit cycle characteristics occur in this IIR system. So now, first I am selecting n, and every duration I am going to calculate what is x of n, and every duration I am going to calculate what is y of n minus 1, that is the previous answer, and I'm going to multiply that with y of n minus 1. For this particular problem, the a is given as 1 by 2. So I'm going to represent that as 1 by 2 y of n minus 1. Once the multiplication is over, it is going to be quantized. So we will check the problem. The quantized bits is 3. So we will verify whether the multiplied answers are having only 3 bits. If it is more than 3 bits, we are going to perform the quantization. And finally, we will add this x of n with this quantized value. So I'll get this answer y of n. So I'll start from that origin that now. So I'm choosing that n is equal to 0. So x of 0 value is given as 0.875. So I'm going to apply this x of n is 0.875 because n is equal to 0. In the given representation, it is mentioned as 0.875. Y of n minus 1, that is y of 0 minus 1. So for this y of minus 1, we don't have any past value. So we are going to substitute that y of minus 1 is 0. So since y of n minus 1 is 0, 1 by 2, that multiplication is going to be 0. There is no quantization required because the available term is only 0. So now we are going to add this x of n, that highlighted term, that x of n into quantization of a into y of n minus 1, that is 0.875. It is going to be added with 0. So we will get this answer is 0.875. It's over. Now for the second time, I am choosing 1, x of 1. But in the given representation, it is clearly mentioned x of n value is 0.875 only at n is equal to 0. So when you have that value greater or lesser or if not equal to 0, the x of n is going to be 0. That is mentioned as 0 otherwise. So we are going to substitute 0 value for x of 1 and y of 1 minus 1, y of 0. So at n is equal to 0, we got y of n. That is y of 0 value, we got it as 0.875. So we are going to apply that is here. So y of n minus 1 is 0.875. So now we are going to perform 1 by 2 into y of n minus 1. That is 0.4375. Now we are going to perform the quantization. So before performing the quantization, first we need to convert this into binary. If the binary value is less than the available bit, that is 3 bits, we don't need to perform this quantization. Otherwise, we need to perform the quantization. That is either truncation or rounding is required. So here I am going to perform the rounding. Even truncation is also applicable. So now I am going to select. I am parallelly doing it here. I am having 0.4375. First, I am going to convert this into binary. So 0.4375 into 2, that is equal to 0.875. So 0.875 into 2. 1.75. 0.75 into 2, 1.5. 0.5 into 2, 1.0. So now the binary representation for this one is, I'm sorry, 1 second. So now the binary representation for this one is 0.0111. Now we need to convert this into 3 bits because that available term is having 4 bits after this fractional point. We need to convert that into 3 bits. So I'm going to perform this rounding. So for performing the rounding, I'm selecting that last bit. If the last bit is 1, I'm going to add with the previous bit. So I'll get the term as when you are adding this, you will get this value as 1 0. So 0 will be present. That 1 is going to be here the carry. So again 0 1. So when you are adding, you will get the value as 0.100. So again I'm going to convert this into decibel. So that is 0.1 into 2 power minus 1. So that is equal to 0.1 by 2. So this is equal to 0.5. So we have got this representation, right? That decimal value is 0.5. So the quantization answer 0.4375 is quantized and we got it as 0.5. So now y of n is x of n, this quantized value. X of n is 0 and the quantized value is 0.5. So we have represented that y of n is 0.5. So now for the next duration 2. This value is x of 2. We already know that x of n value is 0.875 only at n is equal to 0, 0 otherwise. So I am going to apply 0 here. Now y of 2 minus 1, that is y of 1. So for 1, y of n, that is y of 1 value is 0.5. I am going to apply that here. So 0.5, you're going to divide or you're going to multiply that with 1 by 2. So 0.25. Now we are going to perform this quantization. That is, we have the term 0.25. Multiply that with 2. So 0.25 into 2 is 0.5. 0.5 into 2 is 1.0. So this is equal to 0.01. So only 2 digits. So you no need to perform this rounding because that is if we need to perform the quantization, the bits are more than 3. But here only that available bits are 2. So we no need to perform this quantization. So when you are converting this into decibel, again you will get it is 0.25 only. So I can directly write this answer as 0.25. So now the y of n is equal to this x of n. Right? This is with this x of n and this quantization value a into y of n minus 1. That is 0 and 0.25. When you are adding, we will get this answer as 0.25. Now the next one, because till now we don't get any repetition, right? So next value I am choosing that n is equal to 3. So when n is equal to 3, again x of n is 0 because it is clearly mentioned at n is equal to 0 alone we have the value 0.875. Remaining all the places we have the values are 0. So I just substitute 0 here. And now this value y of n minus 1, that is y of 2 minus 1 is y of, I'm sorry, 3 minus 1 is y of 2. For 2, that previous value is 0.25. So we can substitute that value here. So 0.25. 0.25 into 1 by 2, that is 0.125. So we are going to perform this quantization. So I am selecting 0.125. First I am going to convert that into binary. So 0.125 into 2, that is equal to 0.25. 0.25 into 2, 0.5. 0.5 into 2, it is 1.0. So this is equal to 0.001. So the available bit is only 3. So that up to 3 bits, we no need to perform this quantization. If it is more than 3 bits, we need to perform this quantization. So this is equal to again 0.125. So again, I am rewriting this quantization value as 0.125. Now we need to add this x of 0 with this value. So this is equal to 0.125 only. Now the next numeration, that is limit, I am applying for x of 4 value is 0 and x of 4 minus 1, that is x of 3. So I'm sorry, y of 4 minus 1, that is y of 3. So for 3, that y of n value is 0.125. So I'm going to apply that 0.125. When you are performing 1 by 2 multiplication, we will get the value is 0.0625. So now we need to check that available bits. If it is more than 4, we need to perform the quantization. So I'm selecting 0.0625. So 0.0625 into 2, that is equal to 0.125. 0.125 into 2, that is equal to 0.25. 0.25 into 2, that is equal to 0.5. 0.5 into 2 is equal to 1.0. So the 0.0625, the binary representation is 0.0001. So now it is 4 bits, but then the quantized bits are only given as 3. So I'm going to perform this rounding. I'm just checking the fourth bit. If the fourth bit is 1, I'm going to add with the previous bit. So this is equal to 0.001. So now I need to convert this into decibel. So 0 into 2 power minus 1 plus 0 into 2 power minus 2 plus 0 into, I'm sorry, not 0, the third value is 1. So 1 into 2 power minus 3. So this is 0 plus 1 by 8. So that is equal to 0.125. So 0.0625 was quantized to 0.125. So now after quantization, we have got the value is 0.125. So now I'm going to add this x of n with the quantized value. So I have got this answer is 0.125. Next, I'm going to select the next limit, that is 5. The available input is 0. The previous answer is 0.125. When I'm multiplying with 1 by 2, I got 0.0625. And when I'm performing quantization, I'll get 0.125 again. And you're adding, I'm getting 0.125. So now, when you are after increasing the time, that is whether you are increasing 7, 8, 9, 10, all those places, you will get the answer is 0.125. So this output is oscillate between a fixed range of signal 0.125. So this is called as limit cycle oscillation. We cannot say that third value because all the row values are matching only from the 4. So we can say the limit cycle started from n greater than or equal to 4. Now I need to explain one more thing, deadband. In the limit cycle oscillation, the amplitude of the outputs are confined to the range of value which is called deadband. That is the 0.125 for this particular problem. It is confined to the range of value which is called deadband. We have a formula for find the deadband. That deadband is equal to 2 power minus b by 2 into 1 minus modulus a. So for this particular example, the bits are 3. That is, we quantized the 3 bits and 2 and 1 minus a. That constant multiplication we have did is 1 by 2. So when you are doing this multiplication, you will get this answer is 0.125. So this deadband, this value, right? That limit cycle oscillation, the amplitude of the output is confined to a range of value which is called deadband. So I hope you are clear with this limit cycle oscillation. Thank you.